Okay. Hello, everybody. I'm going to be basically rebroadcasting my lecture notes from yesterday because I realized after the fact I probably had my microphone on mute. I hope it's that anyway. I can confirm that I'm seeing the audio levels on my end. So if the audio doesn't come through this time, then we will be looking into what Blackboard Connect is doing here. Okay. So yesterday I was talking about compound interest. And compound interest is very much like simple interest in that simple interest, what we did in simple interest was we decided on an interest rate and we calculated how much that was. And then we just stuck with that same interest amount. For example, if I did a simple interest every month for a year, I would calculate up front how much the interest would be every single month. And I applied that exact same amount of interest every month. So if I earned $10 of interest in the first month, I'd earned $10 of interest in the second month, et cetera, et cetera. In compound interest, right, by contrast, the interest will be recalculated every time we calculate interest. That's called the compounding frequency. So I could be compounding every year, in which case I would only recalculate my interest once a year, or I could compound every month or even more often. In that case, I would recalculate that interest amount every single time interest came due. And if you didn't take the money out of the account, then every time you got interest, there would be more money in the account. So you would earn more interest, right? Interest leads to more interest because what we'll see in a minute, we'll call the interest on interest effect, right? Basically, I'm earning interest on the interest that I earned last time I earned interest, right? So that's what we call the interest on interest effect. And that's the net result of compounding. The first example I did yesterday was one $10,000. The present value, remember in bank account terms, we usually call this P, right? That's what we called our P, $10,000. The interest rate was 8%, and I had to specify 8% APR because now that we recalculate the interest every time we do this, it gets a little bit more complicated. And in simple interest terms, I could just tell you it was 8% simple interest, end of story. There was no confusion. But now with compound interest, well, that 8% is going to be a little different depending on how we calculate. And the default for this kind of calculation will be the APR calculation, annual percentage rate, APR. And what that means is that if I, over the course of the year, I'm going to earn 8%. Now, if I break this up, if I'm calculating interest twice a year, then it won't be 8% every time, it'll be 4%. That way, over the course of the year, I will earn 8% APR. If I'm dividing it out every month, then that 8% would have to be divided by 12. We'll see in the formula in a minute that that's going to cause a fraction, right? That fraction is not going to concern me too much just because I know that I'm going to have a calculator to help me with this. Right? I'm more concerned about knowing how to use the formula than I am about the actual calculations, again, because I know I have a calculator for this. In my first example, I chose to compounding annually. So that wouldn't need to be divided out at all. There would be no fraction in this first version, this first example. And the t-value, how many years, right? I chose to let that kind of go. I think we did a couple of years worth, 0, 1, 2, 3, 4. Right? And the future value, right, that's what we want to calculate. We called that A in bank account terms, right? The accumulated amount or the final balance. And what I did was I set up a little table, T, PV, big I. Remember, big I represented the amount of interest in dollar terms that you earned and future value. And rather than make this a big, long 4-year, 3-year, present value at the very beginning, future value at the end of 3, I'm treating each year, each time I calculate interest, as new present value, future value situation. So if I started with $10,000 in the very beginning, I called that T equals 0, right? Before any interest is calculated. Right? That was technically my value in time period number 0. But I mainly did that to show you that it will wrap down to the next line. Future value becomes present value in the next time period. But I started with $10,000. I went to my calculator and I asked, hey, calculator, what is 8% of $10,000? $10,000 times 8%. That 8% is a decimal, 0.08. Oh, not that. I know that. $10,000 times 0.08. There we go. $800. That's the number I was looking for. That's the amount of interest that I earned during the first year. So I added that together with my present value at the beginning of the year, $10,000. $10,800 end of year one. That wasn't so bad. Now, this is where the compound part comes in. Rather than adding another flat $800 for year number two, I'm going to recalculate it, rolling in the final balance from the previous year into the new present value. And that me down that 10,800, it come down to the next. So this is now the amount that I'm going to calculate with. So even though I'm earning the same 8% interest during year two, that 8% is bigger because the present value, because the PV is bigger in year two. So let me take my new present value, 10,800, it's already on my calculator screen, and let's multiply this number times 0.08. You see the amount of interest that I would earn during the second year would be $864, right? It's bigger than the previous amount of interest. I'll add that back into the total, which remember I started with 10,800. So let me add that to 10,800, which means at the end of year number two, I will end with $11,664. Again, it's neat, right? It shows that the amount of interest I'm earning is going up. And if I wanted to repeat this process, right, that $11,664 becomes my present value in year three. And that's me wrapping it around here for year three. I would multiply this number times 8%. So I'll bring up my calculator. $11,664 times 0.08, one more time, gives me $933.12. So I add that $933.12 to what I started with, 11,664, which gives me a final value after year number three of $12,597.12. And the neat part about this, right, is that this interest amount is going up because I'm earning interest on the interest, right, that I previously got. And you can even see that. You can think of, if you wanted to sort of mentally subdivide this down, that 8% of 10,000 is 800. That was the initial amount of interest. So that must mean that how much interest am I earning on the interest that I calculated from the first year? Well, that's $800 of interest from year one, and it earns 8% interest on its own now during year two, the extra $64, right? You see how the difference between year one's interest and year two's interest is $64? That's the extra $64. That's the interest on the interest from year number one. Now, as we keep going, that would be much more difficult to keep track of because not only am I earning the $800 of interest from my initial $10,000, I'm earning the 8% interest on year one's interest. That's $64 extra. And I'm earning 8% interest on years two's interest. So that's $864 times 8% again, $69.12. And right, I'm adding all of that stuff together. And so it's much harder to keep track of the interest on interest effect, but we can clearly see that it's happening, right? I've got this snowball effect going on. And students ask me, Professor, is that interest rate going to keep, or not the interest rate's been the same the whole time, but is that big I interest amount going to keep going up forever? Yeah, it will. It'll keep going up literally forever. Um, and so that's the power of compound interest. This is a great thing, right? If you have a savings account or some kind of investment, you've probably been on the other side of this, though. This is the same way that credit card accounts work. If you've known anybody that feels trapped under a lot of credit card debt, that's probably why, right? It's growing at compound interest, and it's not like the compound interest rate that the credit cards will offer you is that generous, right? Your credit card might be 15% APR. It might even be higher than that. It might be 24% APR. I've seen some credit cards offer 29% APR. Oh, wow, a big interest rate, especially if we're talking about this compounding interest on interest effect. So after we did that first example and saw some of the neat growing effects of compound interest, I went on to look at, well, what is the actual formula here? I used the P's and the R's the same way I would in the simple interest formula, just because I wanted to make it feel familiar. Right? If you notice, the very first formula that I have up here, P times 1 plus R, is a simple interest formula. Right? It's just that T is equal to 1, right? I did it for 1 and only 1 year. So that's P times 1 plus RT. I plugged in T equals 1, and I got that P times 1 plus R. And I said that P times 1 plus R, you're going to see quite a bit. Right? That 1 plus R represents the fact that I'm getting the money I got, right? I'm getting back I started with. That's the 1 part. And I'm getting a little bit more in interest. That's the plus R part. You can imagine doing distribution here, right? If you distributed that P to the 1 plus R, P times 1 is P. That's your initial principal back. P times R is the extra interest. So that 1 plus R represents me earning interest on the amount that I started with. And because that amount rolled down, because this final value became the present value in year number 2, right, this entire thing, this entire formula came down and filled the same place that quote unquote P would represent in the next line. But because that was already P times 1 plus R, I ended up with P times 1 plus R times another 1 plus R. I see the same thing twice. And it's not like that would get any better, because during the 3rd year, all of this rolls down. So all of this would roll down as well. All of this would roll down and fill in what would be the principal during year number 3. I multiply by another 1 plus R. And if I haven't scrolled down yet because I didn't want to give away the game, but mathematically we have a word for multiplying by the same thing multiple times. And we saw it last week. That was exponents. Can't I express this same idea with exponents? Wouldn't this be P times 1 plus R, right, to the first power? Wouldn't this be P times 1 plus R? Sorry, I didn't want to write a capital R, but I kind of fell into it. To the second power? There's 2 of them, right? Wouldn't this be P times 1 plus R to the third power? And it would keep following that pattern all the way down. It looks like the exponent on 1 plus R matches the time period 1, 2, 3. Right? 1, 2, 3 matches the time period 1, 2, 3. And that's not a coincidence. We'll use that, excuse me, just trying to get rid of the extra marks. We'll use that in our formula. Now I'll scroll down and show you. The compound interest formula looks very much the same as the simple interest formula, but instead of P times 1 plus RT, right, it's P times 1 plus R raised to the exponent T. And that's the big difference between the two, right? If you were to look at simplest in a graph, right, it would be a perfectly straight line. It even half looks like an mx plus b kind of formula in the middle there, right? If you look at it, doesn't this kind of look like an mx plus b thing, right? Our t will be the variable, right? What we're going to allow to change. Right? That r kind of represents the slope, right? And if you looked at it in a graph, it would be the slope of the line, right? And that p just makes everything a little bit bigger. But now, with the exponent, that graph would look significantly different because that graph, whatever it looks like, it's going to get steeper and steeper and steeper, right? Because this amount of interest kept getting bigger and bigger and bigger. So we would be able to see that snowball effect in the graph, right? It would start somewhere and it wouldn't be a straight line. It would curve up and it would keep curving up faster and faster and faster and faster. If you zoomed out far enough, you would be able to see this very distinctive shape of the exponential graph. That's what happens. And that's the reason why some people find themselves in a lot of credit card debt, because they're on the wrong side of this curve, right? They've kind of rounded that bend and now it's starting to get out of control. Right? On the flip side, right? Again, we'd like for this to happen if we're the ones having money in the savings account or we're the ones investing. We'd like to be on that side of the curve, right? If it means that all of our investments are growing at a very, very large rate. And the power of compound interest. That version of the formula, I don't use it that often. It does match with my understanding of simple interest. Normally, when I'm using the compound interest formula, I will use slightly different letters, though. Right? I have two versions here. The top one, the top version of this formula is what I usually use. P times 1 plus I, little I, to the n power. And when I use these letters, right, the I will be the interest per period, and the n will be the total number of periods. Looks like my writing got messed up. I'll rewrite that one. The total number of periods. The nice part about that is that I can just calculate the interest per period when I need it. Yes, sometimes that will be a fraction like we saw earlier. If I needed to divide that 8% out into a couple of different sub payments, I would divide it. I would have a fraction, and that's okay. Right? I would much rather remember this easier version of the formula, right? One that you see below it that has the big nasty fraction already in it. Right? N, likewise, I'm going to have to keep track of how many periods that is. Right? If I give my interest rate per year, but I tell you I want to calculate per month, I'm going to have to remember that that's 12 months per year, 12 times 1 year. So yes, it's a little bit harder because we have to remember what we're actually talking about. But I kind of think that remembering what you're talking about is actually really beneficial, right? The more you do that, the easier it will be. It's not like once you memorize this bottom formula, which is the same thing, but you notice instead of I, whoops, highlighter please, instead of I, they have this R over M fraction, and that's assuming that we're talking about a yearly interest rate, the APR, and subdividing M number of times. Right? And so that's why the R is the APR. It has to be the APR in this version, fraction version of the formula. Right? And just like before, right, M times T, that's the number of subdivisions times how many years. Well, if you multiply the number of subdivisions times the number of years, that tells you how many times you're compounding, the total number of periods. These formulas are the same, but like I said, I don't think that memorizing the fraction version of this formula will be super beneficial in the sense that, yes, it's a little easier to plug in numbers, but it's harder in the sense that if you don't know which numbers you're plugging in, how are you supposed to use any version of this formula, right? The easy one or the hard one? Well, I call them the easy one and the hard one. Right? Some people may really identify with the fraction version of the formula. you may have actually used the fraction version of this formula when you were in high school or in a different math class. Right? There's nothing inherently wrong with the fraction version of this formula. I just don't like to use it because we've got a couple more formulas coming up next week, maybe even tomorrow or later today. For annuities, they will look fundamentally the same as the compound interest formula if you use the P equals 1 plus I version of the formula. They'll look very familiar. So I'm going to use the P equals 1 plus I version of the formula. Second example. It looks like in this second example, I started with $5,000 and I did 5% APR compounded monthly, right? And that became an I value of 5% subdivided into 12 equal payments. That's why we have that fraction, 5% subdivided into 12, 0.05 over 12. And I let that grow for 15 months. Here I gave the number of periods specifically. That's why the n value didn't need any weird multiplication business happening. I gave the number of months outright. Notice how the time period and the compounding period must always match. We can't do this if they don't, and I will never give you a problem with the time period on the compounding and the does not match. Right? Or at least if they don't match, you're going to have to make them match. Wrote down my formula, A equals P times 1 plus I to the n power. Most of the numbers could plug straight in, right? P plugs straight in. The fraction for I plugs straight in, right, now that we knew it. And n plugs straight in. Now, if you notice, I went straight to the answer here without giving a lot of work. And the reason I was able to do that was I was using Desmos Scientific Calculator to do that. And I encourage you to do the same. If you do not have a calculator of your own, it's a good idea to have one. But if you don't have a calculator of your own, use Desmos Scientific Calculator. And that's just, you can see it, you probably can't see it on my screen. It's desmos.com/scientific. Desmos.com/scientific. And it's a pretty good little calculator here. So I needed to type in 5,000 times 1 plus 0.05 over 12, all raised to the 15th power. And I can do all that in Desmos. 5,000 times 1 plus 0.05. When I press the divide key, it makes it a fraction. That's awesome. Over 12. I'm going to use the right arrow key to get outside there. Raised to the power of 15. And I don't have to do anything there. The Desmos calculator automatically knows the correct order of operations, and it follows those steps, right, in the correct order to give me a decimal answer you see on the right side, 5,321.781228. Okay? Since we're talking about money, our money is rounded to 2 decimal places. So I made that $5,321.78, which is what you see right here on my page. It works out really well. I'm going to encourage you to use a Desmos or equivalent scientific calculator for all of these problems on test 1. Super helpful. Okay. On the right side over here, I did the same thing again with the fraction version of the formula. Okay. You can see that the fraction version of the formula wasn't really any harder, but it did help me figure out what fraction to put in there, right? So I had to figure it out for the I, but it looked very much already like a fraction. But I had to do this weird nonsense with the number of compounding periods here, because the 12 was there because I'm compounding 12 times a year, but I said 15 months, and that's really hard to plug in. Right? The t value in the fraction version of the formula has to be years. And so I actually had to do this dumb fraction time period, right? 15 months divided by 12 months per year. That's a fraction number of years. And yeah, you can see that the 12 and the 12 would cancel out of the fraction, and it would just leave 15, which is exactly the same as the 15 from back over here. But I'm not a big fan of using, like I said, the fraction version of the equation, of the formula. It would give us the same result, which is why I didn't write down the result a second time. Let's see. In this example, it stops there. Right? Investing $15,000 for 9 years at 4% interest compounded quarterly. You see my little note here is that if I don't tell you what kind of interest this is, you can assume that it's APR interest. That, remember, APR was a yearly interest rate, and it was compounded. I have to give you the compounding frequency here. I told you it was compounded quarterly. And we'll talk about the other version of interest probably next week. It's called the APY. We might even do it at the end of the annuities lecture. But if it's not specified, you can assume that every interest rate is an APR, and you can subdivide that out as equally as you need to. 4% compounded quarterly tells me that's 4 times per year. So I got my fraction here. That's 4% over 4, split up into 4 equal interest payments. And because I'm going for 9 years and I'm talking quarterly, well, how many quarters is that? Well, that's 4 per year times 9. It's going to end up being 36 quarters. But I'll show you how you have to type that into Desmos if you choose to do 4 times 9. All of that goes straight to Desmos. 15,000 times 1 plus 0.04 over 4 to the 4 times 9. Oops. I need to press enter. 15,000 times 1 plus 0.04 over 4, right arrow, close my parentheses, raised to the power of, if I tried to do 4 times 9 right now, you see how it goes out of the exponent? You can't stop it from doing that. So if you want to type 4 times 9 in the exponent, you're going to have to do 4 times 9 with parentheses. And that's okay. There's nothing wrong with that. Right? Although a lot of students might say, you know what, screw all that. I just know 4 times 9 is 36. I'm going to type in 36 directly. Either way is okay. Right? Again, the good part about this is that we don't have to keep track of the order of operations. As long as we type this into the calculator correctly, it's going to do all of that nasty arithmetic that we really have better things to do than arithmetic in this class. $21,461.53, rounding to 2 decimal places. It's pretty neat stuff. Right? If we were always calculating the future value, the A, right, that would be the end of this lecture. Right? But we're not always calculating the A. Right? Sometimes we'll need to calculate the P. Sometimes we need to calculate the I. Sometimes we need to calculate the N. Right? And what I did down here is basically go through a little bit of algebra to find all of those things. Right? I'm going to, because I did all of these next to each other and I didn't write them all down at one time when I gave this lecture the first time, I'm going to pull your attention up here first. Right? So here is the regular formula, A equals P times 1 plus I to the n power. And if I wanted to solve this equation for P, right, you might tell me, hey, just divide by that big set of parentheses, professor. Right? I divided it on both sides, and it canceled on the right side. And I see it down here in the bottom of this fraction. Okay? Absolutely. That's something I could type into the calculator. But I don't like typing big fractions into calculators unless I absolutely have to. So I'm going to borrow a trick from other parts of math. I know that exponent rules tell me I can bring that up to the top of the fraction if I want to. I just have to make sure when I do that, the exponent is negative, which is why you see in the bottom I brought it up. There's no longer a fraction, but I made it a negative n. The negative n power makes a lot of sense to me, because if you compare the negative n version of the formula with the positive n version of the formula, you'll see that, right, I'm calculating the p, right? I'm basically starting with the a, the future value, and I'm going back to the p, which is the present value, right? And doesn't that mean I'm going backwards in time? Shouldn't it kind of make sense that my n value, which is a time value, is negative in this case? That negative kind of represents me ungrowing the final value back to the initial value. And so I like this version of the formula because it kind of makes sense, right? It meets my intuition for what this is really doing. So if we need to solve for p, there's a formula, right? And again, I don't encourage students to memorize that formula, right? It's hard enough to memorize the original version of the formula. I say just do the division every time, right? You don't have to show it in two different steps, but if you think in your mind, hey, I need to divide by that set of parentheses, oh yeah, I'll make that a negative exponent, then you won't have to write that out every single time. Yes, I encourage you to write it out once or twice, but the more you practice this, the more you do it, I guarantee you'll start going, oh hey, I remember how to go from one to the other. I don't need to show that every time, but thinking about that little one step of algebra, I think is better for your mental, your math hygiene, your math skills, right, than just dumping a big list of formulas on you and hoping that you memorize which one is appropriate. I don't like that. You probably know my style by now. That's not me. So if you need to solve for p, here is the p version of the formula. P times a, 1 plus I to the negative n power. Go up here. What happens if we need to solve for I? Now this one's a little more complicated because the I is inside the parentheses and it's being raised with an exponent. And here's where I'm going to use the mathematical tools that we talked about last week in homework C3 to help me with this. This looks like an exponent base power kind of relationship. This is exactly what we did in homework C3. The only challenging part here is that I've got that extra p, right? Because that p is not in the base. Right? So what I did is I first divided by p. Yes, that makes a fraction, but I'm not too worried about that. Again, fractions are just fractions, right? I'm just going to let them be what they are, right? I'm going to go in my calculator in the end anyway. So I'll let my calculator deal with that. It's a fraction, so be it. When I get down to here, a over p equals 1 plus I to the n power, this looks exactly like my base exponent power equations from last week. And if I want to solve for I, which is in the base, right? If I'm solving for the base, I need to use a radical. That was what we talked about last week. So let's turn this into a radical. Right? The base is what I'm solving for. The exponent became the index of the radical, the little number on the shelf, and the power became the radicand. It went inside the radical. That's how we did it. And that's almost exactly the formula I need. The only thing I needed to do was get rid of that 1, because you see it's 1 plus I on the left side. So I subtracted 1 from each side of the equation. And that gave me this formula here. I equals radical, that's the nth root of a over p, all minus 1. That minus 1 is outside the radical. But I could type that into the calculator. I know that looks super complicated, right? Or maybe not super complicated, but it looks like something I wouldn't want to do myself. But my calculator will be able to do that for me. I just need to know which buttons to press. On the Desmos calculator, I can type in, right, any radicals that I want to. Right? The button is right here. sorry, I don't need two of them. And I could type in, if I was doing 12, I'm just making up some numbers at this point. There we go. I'm going to go use the right arrow to go outside. Oh, yeah, that's not outside, so let me go back. Right arrow again. Outside to get that -1. That would be my I value. And notice that the I value is already, it's a decimal which represents a percent. So if I were talking what percent is that, I would move the decimal twice. That looks like 16.668%. And I would round that however the problem told me to. Okay. Sometimes the problem is going to make you multiply that out. Like for example, if this were a thing, right? Your I would normally be divided by 12, right? So you'll have to multiply that answer times 12 to get a yearly interest rate. We'll see some examples, I think, in our homework. But again, this is the I version of the formula. I don't encourage students to memorize this. I instead encourage students to write down the original formula and think, okay, I need to shuffle this around. The A over P is going to be a pretty common thing. So again, you don't have to write this out in 4 separate steps, right? But just knowing that you need a radical, you're already 90% of the way there. So if I'm solving for I, which is in the base, I need a radical. Here's the last one. If I'm solving for n, remember I've already solved for a, I don't need to do anything for that one. But if I'm solving for n, now that's the exponent. Well, if I'm solving for the exponent, that's a logarithm thing. That's what we learned last week. So I'll start by doing the same thing by dividing by p to make it look specifically like a base exponent power relationship. And then I'll use a logarithm. Now this logarithm looks a bit silly because the base is 1 plus I, and it looks really weird to write all of that down in the base. And even worse, Desmos calculator can't handle a complicated base like that. And so if I'm going to ask Desmos to help me, I'm going to need to use what's called the change of base formula, because Desmos calculator can only handle 2 kinds of logarithms. Logarithm base 10, which is the LOG button on the calculator, and logarithm base E, which is the LN button on the calculator. We don't need to work with E too much in this class, right? Suffice it to say it's a super important calculus number, and it forms the basis of so many things that you'll see it very often, which is why it gets its own button on the calculator. You don't need any other logarithm bases than these two. Technically, you only need one of them. It's just that both of them are so commonly used, they both get buttons. Any other base that you want to use will have to use what's called the change of base formula in a scientific calculator that can't handle bases. Basically, what we're doing is we're dividing 2 logarithms. Right? The kind of logarithm that you're dividing, as long as it's the same on the top and the bottom of this fraction, it doesn't actually matter. So you could do log divided by log, and it would be the same thing. But I'm doing logarithm of what was inside the parentheses divided by logarithm of the base. This is something the Desmos calculator can help me with. That's called the change of base formula. And again, I'll just type some random numbers into this. I would have to do the ln button on the Desmos calculator is over here under functions. Function ln, let's say function ln 25, close parentheses, divided by function ln of, I don't know, 15. There we go. And so that's the same thing as logarithm base 15 of 25. Okay. We were allowed to use it like that. Again, Desmos does not understand if I tried to type in my own base. So we would have to do that manually. Some calculators, like the calculator that I have sitting here on my desk, I have a Casio FX115 ES Plus. It actually has a special button that lets you type in your own base. And so I could type it in exactly the way I've seen it here on the left side with that 1 plus I. I'll plug in a number there, of course. It would even have a silly fraction. Right? I could type all of that into my Casio calculator and it would handle it. It's only the Desmos calculator or other calculators which don't understand logarithms of other bases that we have to use this change of base formula here. So we have several versions of exactly the same formula, depending on what I want to solve for. If I'm solving for the I need a logarithm. Or excuse me, if I'm solving for the I need a radical, because that's part of the base. If I'm solving for the n, I need a logarithm, because that's part of the exponent. And if I'm solving for a or p, because they're outside of all of it, I don't need either. I just need exponents, right? But a positive exponent for the a, negative exponent for the p. I gave a couple of examples here. I just filled in this table with the numbers, the a, the future value, the p, the present value, the interest rate I per period, and the number of periods n. And we practice plugging these things into our calculators. Right? I'll scroll down to see. So here's what we did. The first row, this top equation here, right? I always write down the equation first. I plugged in 5,000 for A, 0.02, which is 2% for I, and 10 for N. Right? If I were making that a word problem, that might be investing. I wrote 50,000 in the table, but 5,000 down below. So here's what I'm going to do. Whoop. That extra zero was never there. $5,000 was invested at 2% APR for, no, that's not 2%. Yeah, 2% APR for 10 years. See, I had to make sure that the 2%, that interest rate matched the time period for N. So I could say 2% APR, which is a yearly interest, for 10 years. Or I could say 2% every single month, which doesn't need to be subdivided, for 10 years. And there's lots of different word problem variations I could do on that. But the main thing is that my I time period matches my N time period. I plug it into my calculator, find the p-value. But because I wanted this p-value, I had to use the negative exponent version of the formula. And I plugged in the negative exponent version of the formula into the Desmos calculator. It has no problem dealing with negative exponents. We've already seen one like that. $4,101.74. For the second row, we had to do a little bit more work because we were solving for N. And I plugged in my A, I plugged in my P, I plugged in my I. But when it came to N, right, that was where the logarithms came into play. Okay. So I plugged in all my numbers after writing down my formula and my equation. I always do that. I plugged in all the numbers and I started working with it. I knew that because I'm solving for N, I need to use a logarithm. I divided by that 6,000. Now, 9,000 divided by 6,000 is kind of a weird fraction, 9,000 over 6,000. I asked my calculator to help me with 9,000 over 6,000. My calculator can reduce fractions for me. I believe the Desmos calculator only gives you a decimal. So I don't really use the Desmos calculator. Oh no, it will. See this button over here? That says Desmos calculator, give me a fraction for that. So it knows that that's the same as 3 over 2. So you can actually have the Desmos calculator help you with your fractions too. Excellent. I forgot that it did that. So I use 3 over 2, just easier for me to type into the calculator. Okay? If you wanted to type in 9,000 over 6,000 in every line after this one, you certainly could. And some people get paranoid about, oh no, I don't want to mess up the fractions. I'm just going to keep the big numbers. That's fine. So let's see. When we changed this to a logarithm, we took the base, it's that big nasty 1 plus I with a fraction. Ugh. But all of that was the base. And what's inside the logarithm was the power, 3 over 2. Again, if you have my Casio calculator, you could type this in directly to the Casio calculator and press enter. Desmos calculator does not understand a logarithm with a fancy base like that. So what I did was I split it into a fraction. The old insides on top, the base on the bottom. That's how I remember it, by the way. The base goes on the bottom. B for base, B for bottom. And I made them both LNs, which the Desmos calculator does understand. So let's see. Let's type in ln. That's also under the functions tab up here. So, oh, I already said that. ln of 3 over 2, close parentheses. Oh, no, right arrow parentheses, divided by ln of, see, what was it? 1 plus 0.03 over 12. 1 plus 0.03 over 12. Too far. Here we go. 1 plus 0.03 over 12. Right arrow. There we go. That's what I was looking for. Again, thank goodness I don't have to do that manually. And we've got calculators for this. This gives me the in value. And depending on exactly how long the time period that is, decimal places for time values start meaning less and less very quickly. I wouldn't ask you to round this to 4 decimal places. Because if you think about it, how long is 1/10 of 1 year? 1 year is about 12 months, so 1/10 of that is maybe a little bit more than a month. So maybe 1 decimal place for years is a good idea. Well, how about 2 decimal places? Well, if 1 decimal place is 1 month, roughly, we divide that into 10 more, that's the second decimal place. That's about 3 worth. I'm not sure 3 days is going to be super useful of a time period. Your bank is not really keeping track of it that accurately, but maybe it is. Maybe they calculate average daily balances. I don't know, 2 decimal places. Definitely not 3 decimal places. 3 decimal places would be 3 days divided by 10. Oh, goodness gracious. That's 3/10 of a day. I don't know. That's every 10th of a day is about 2.5 hours. 3 of those are, maybe 7 to 8 hours. Definitely not. I don't care to calculate my time values that exactly. When it comes to years, I'll probably keep 1 decimal place. When it comes to months and anything smaller than months, I'll usually just ask you to round it to a whole number. It's any of the decimal places would not be useful to keep track of. And I think that's what I did here in the notes. Yeah, I rounded it to a whole number of months, 162. And technically, if I wanted it, be careful on the word problem wording, because if I said my future value needed to be at least 9,000, then I would really need to round this up to 163, right? Because if I get to 9,000 somewhere in the middle of the month, then it won't, right? If I round it down to 162, then I'm not at 9,000 yet. Right? So a lot of times, depending on the wording, right, you might say, okay, well, look, I need to have at least 9,000. So I would always round up, even though it's 0.39, I would still round up. The 163rd month is the very first time that the value will be greater than 9,000. And anytime before that, it'll be slightly less than 9,000. So here's the chart that I ended on. I didn't do an I one, a radical one, because I kind of ran out of time before. But this is a nice thing to remember, right? The simple interest was a perfectly straight line because the amount of interest that you earn every month is exactly the same, right? That's why it has this sort of slope idea. Every month or every time period, you earn the exact same amount of interest. And so that is the slope of this line, right? The R represents the slope of this line. And if I followed the value over time, it would be a perfectly straight line. Compound interest was different because I'm recalculating that rate every single time period. So now it's not just 8% of what I had at the very beginning, it's 8% of what I have every time period. So that's why, right, at first, it's small, it grows small, but the farther I go, the more and more it becomes every single time, right? That's the snowballing interest on interest effect. And that shape is characteristic of exponential relationships. We don't study them too much in this class. We did a little bit last week. We'll do a little bit this week. Right? But that's about as far as we'll go with exponential relationships on the sort of theory side. But all we need to know is that it's snowballing, right? And it's getting faster and faster. Annuities, which is what we'll do in the second half of the lecture, they're going to be the same as compound interest, but unlike compound interest that we did during this part, where the present value was always the same and it did go up, but only because of the interest that kept getting added into it, right? We are actually going to deposit a little bit more every month or every time period. Right? That's what these vertical jumps are, right? On this version, right? These vertical jumps represent me putting more money into the account. And that's not extra money that came from interest. That's extra money that came from me putting more money into the account. And so in between the jumps, it does follow a compound interest exponential curve, but every so often it's got a perfectly vertical jump straight up. And that's what happens when I put more money into the account. It perfectly jumps straight up. Right? Again, we won't graph these things. I'm only doing this as a intuition for you to say, okay, this annuity, it's going to be compound, but jumping because I'm adding a little bit more. And our formulas will look a little more complicated because we'll have to keep track of all of those extra payments. Do you remember how we said we had to keep track of the interest on the interest? And we were glad that the formula did all that for us? Well, when it comes to annuities, we're going to have to do the same thing. And so hopefully we'll have a different formula which keeps track of not just the interest that I earn on, right, the initial amount, but also the interest that I earn on this first extra payment and the interest that I earn on the second extra payment, right? Right? And the interest that I earned on the interest that I earned on the, you see how it gets really complicated really quickly. Hopefully we'll have another formula, right, to deal with all of the extra interest that happens in this annuity situation. And I'll take a break here. I'll probably go have something and come back and record the second half, which I'll call the B part of the lecture. We'll do the annuities part. Hopefully the audio worked this time. I will see you next time.